Hi, today we're reviewing Section 2 of Unit 2, Building Molecules. So if you're building a molecule, you want to become familiar with ball and stick models. Ball and stick models give you some more information than a structural formula would be because it moves it to more of a three-dimensional model. Notice that these are not all in a straight line. This is because the atoms are moving as far away from each other as possible to create the least amount of electron repulsion. Electron domains in section 210 is highlighting the areas of electron location and how those domains move away from each other to minimize electron repulsion. Notice this is a carbon. Remember, in the Honk rule, carbon likes to bond to 4 atoms. In this case, those 4 electron pairs or domains move as far away from each other as possible to create this shape. Over here for nitrogen, even though it's bonded to 3 atoms, there is a 4th pair of electrons that also takes up just as much space as the other 3 atoms do, and so you have to remember to reserve space for it. This is why ammonia has this shape. Finally, the water molecule here also has 4 electron domains and carries a bent shape because you're making sure that those electron domains that are not bonded are also provided the space that they would need, just as if you were bonding atoms in those 2 locations. In section 2.11, there are more shapes to consider. One would be for carbon dioxide. When you have the double bonds in carbon dioxide, keep in mind that there are no lone pairs above and below the carbon. So you don't create a bent shape. You literally have 2 domains, and in having 2 domains, you can separate them 180 degrees, which is a maximum distance. Below is an example of a more complex molecule, which kind of has some other shapes that you can consider. Again, the common carbon with 4 equidistant bonding domains, which gives a tetrahedral shape. Over here we have 3 electron domains, which creates a flat trigonal planar shape. And finally, looking around this oxygen atom, we have 4 domains. You can't see the 2 hidden lone pairs. However, you can note that there would have originally been 4 domains, and the 2 atoms that are bonded would provide a bent shape. Space-filling models. This section compares ball and stick models with space-filling models. You can see that the space-filling models do not show the double bonds. So that is a problem or a con with this particular model. However, it can provide us a better shape, a better feel for what the shape is and how that might give us some further information about the behavior of the molecule. You can see here in this space-filling model that it kind of looks long and stringy. This one kind of looks like a fry pan with a handle, and this one seems to be all balled up, so we call it ball-shaped. And notice that the shapes are tied to general smells. So long and stringy is sweet, frying pan shape has a tendency to be minty, and ball-shaped molecules have a tendency to smell like a sort of a camphor, which is like a pine scent. Okay. So, rules for determining smells, excuse me, not cells. In summary, sweet smells have a tendency to have 2 or 1 oxygens. It's stringy. It has a tendency to have an ester group for sure. Minty smells typically have rings. Fry pan shapes are typical. Camphor or that pine scent has a tendency to be ball-shaped. Putrid smells are definitely carboxyl groups that you'll see embedded within the carboxylic acids. And finally, fishy, there's always a nitrogen, and the naming is always amine. Again, these are typical ways of determining the smell. They're not 100%, but they are a good average. We finally end this section with the receptor site theory, which basically says that the shape of a molecule will have a tendency to interact with a site in your receptor cells, which signal to the brain that particular scent.